All right, let's go ahead and take a look at a couple examples. We'll use, the first video will be over example 1 on your student example sheet, and then the second video will be over number 2. So go ahead and pause this for a second, read through this information, and make any notes yourself that you need to. Okay, so it says the following data represents the weights in grams of individual candies in a randomly selected bag of M&Ms. So it's randomly selected, so underline that. Use this data to find the sample proportion of M&Ms that are green. So here's the green. And then test the claim that the Mars company, who makes M&Ms, they say that 16% of its chocolate M&M candy should be green. All right, so what I did was, ladies and gentlemen, the first thing is I've given you the data here, and these data represent weights. Now, again, weights are quantitative. When we do proportions, we want qualitative. We want the percent of M&Ms that are green. So really, we don't need the weights here. We just needed to figure out in this bag how many were red, orange, yellow, brown, blue, and green, which I did ahead of time to save some time. That's what the numbers at the bottom of each column are. And then figure out what percentage of our bag is green. So we don't need the weights. We're doing counts, and that's when you do proportions. Typically, you're counting data, categorical data. So if we go through here, let's just write a few things down. If you add up all those numbers, there's 100 M&Ms in our bag. X, which is the number of green M&Ms, because they want to know, they're making a claim that 60% of milk chocolate M&Ms are green. So we have 19 green M&Ms in our bag. So our sample proportion, p hat of green M&Ms, is 19 over 100, which is 0.19, or in this case, 19%. Now, they claimed it was 16% should be green. We have 19%. Now, obviously, there's sampling variability. No matter if you choose a different bag of M&Ms, you'd probably get a different percentage that are green. Now, is that 19% we got due to just sample fluctuations, or is it due to the fact that maybe the bags aren't being filled with 16% of green M&Ms? Is our sample data strong enough to say that maybe it's something other than 16%? Okay. So, with that being said, we've already done the first thing. We found the sample proportion. That's what this is. So let's go ahead and let's perform a hypothesis test. And I'll label each part as we go through it. And I'm probably going to have to go on to the next slide, too, with respect to, I'll label each part with respect to which step it is in your process. So let's do A and B here, where we go ahead and figure out what our population parameter is. It's a population proportion, and then we're going to set the null and alternative hypothesis. Well, the null hypothesis comes from the fact that they say, ladies and gentlemen, don't use a percent here, that the percentage or the proportion of M&Ms that are green is 16% or 0.16. Now, it doesn't say anywhere else whether we are testing whether they're putting too many greens in there or too few greens. We just want to know, is it something other than 16%? So this is going to actually be a two-tailed test. This is not equal to 0.16. Okay, again, we're not saying, are there more greens in there? Are there less greens? We're just saying, is it something going to be, we're testing it if it's different than 16%. Okay, now, let's go ahead and then for C, we need to know what alpha is, and it doesn't really tell us what to test this at. So remember, if it doesn't tell you, you just use 0.05, and I'm going to put that's the assumed level of significance. And then let's look at the requirements. Okay, remember there are 3 requirements in order to be able to perform a hypothesis test. First of all, it has to be a simple random sample, and it did say up here, underlined in blue, that these were random. This bag was randomly selected. Heck, if you go to the store and just pick out a bag, it's going to be a random sample because the bags are distributed at random. So we do have a simple random sample. Now, also the sample size has to be less than 10% of the population size. So how do you figure that? Take 10 times your sample size. 10 times 100 is 1,000. Now, ladies and gentlemen, we know there's more than 1,000 M&Ms out there. So we can safely say that because of this, because there's more than 1,000 M&Ms out there in the population, that our sample size of 100 is less than 10% of the population. So we're okay here. And then finally, you got to meet 2 conditions here, that your sample size times our hypothesized proportion value n times piece of naught. Okay. Now, I'm sorry if it seemed like I cut there. I tried to edit the video and I probably didn't cut it in the best place. But again, I'm just trying to pick up from where we left off here. So what this is, this would be 100, our sample size, times our hypothesized proportion of green M&Ms, which would be 0.16. So that would be 16 times, which is greater than 10. So that works. Then you go ahead and you take, ladies and gentlemen, your sample size times 1 minus your hypothesized population proportion. And that would be 100 times 0.84, and that is equal to 84, which is also greater than 10. Again, if any of these three conditions right here didn't work, then we would have to stop because we can't use a normal distribution. So now let's go to part E then. And I'm going to go to the next empty slide so I can do this. And this, again, is if necessary. You don't have to necessarily draw this if you don't want to. So, ladies and gents, here is our Z distribution. Okay? It's centered on 0 with a standard deviation of 1 again. And go ahead and let's draw. I'm going to draw an alpha. Now, remember, since in the alternative hypothesis was not equal to, then that alpha gets split amongst the two tails. And remember, all alpha is, it's the probability that we falsely reject a true null hypothesis. So in other words, we end up with sample data that's extreme when in essence the proportion of M&Ms is truly 0.16 when our data says it isn't. So we need to take that alpha and divide it by 2 and get 0.025. And do the same over here, ladies and gentlemen. Take that alpha and split it in 2 and get 0.025. Where did I get 0.025 from? Took your alpha of 0.05 and divided it by 2. Okay? Now, let's go ahead and calculate the test statistic. All right? And this would be F. Again, you didn't need to draw the picture if you didn't want to, because we're going to just calculate our p-value from there. But if we do the test statistic, remember that here's the test statistic. P hat minus p sub naught, then times the square root of p naught times 1 minus p naught all over n, and p sub 0 or p naught. Now again, remember in that denominator you use the hypothesized proportion from the null hypothesis. So we go ahead and we put in p hat, our proportion of green from our sample, minus our hypothesized proportion of green, all over. Now here's where you got to be careful. We're going to use the 0.16 from the null hypothesis, the proportion of our hypothesized to be green, times 0.84. Sorry about my writing there. Let's do this. All divided by your sample size of 100. Now, if you be careful with your calculations, remember, don't round till the very end. And then we get actually a test statistic of 0.818. Okay? So, ladies and gents, if we go back here to, and we want to find now the p-value. So, if I'm going to extend this down, extend the page. So that's F. So for G, we want to know what's the p-value for this test statistic and our alternative hypothesis. So, ladies and gentlemen, we go ahead and click out of there, minimize this. You go to your normal distribution, okay, and then we are going to go to find a probability. So if we go to our normal probability distribution here, again, disregard the mean and the standard deviation. We're on a standard normal distribution. So even though we're doing proportions, we're looking at it on a standard normal distribution. Keep those as 0 and 1. We're going to look at our test statistic and go to an upper tail. Why? Because our test statistic was positive. So ladies and gentlemen, we're going to type in our test statistic, which was 0.818. And you'll see right here is our probability value in the upper tail. Okay? Right there as a percent. But again, for the upper tail, that p-value is actually, if you move the decimal 2 places to the left, 0.2067. Now that's the probability that we will get a test statistic, sample data with a test statistic that is more extreme than ours. That's pretty high. Now that's only for the right tail, but we also have to go and put that on the left tail also. And that's what you have to do with the two-tailed test. That's the probability you get a test statistic at least extreme on the right tail, but since it's a two-tailed test, it's not equal to, we also got to add that value onto the left. Okay? So, I'm going to go back to our menu here, or our diagram. This is why the diagram is helpful, is because here's what we calculated right here. Our p-value was larger than 0.025, so it's somewhere up here on the right side. Our p-value on this side was 0.2067, but that's only if it's more extreme on the right. Again, this was a two-tailed test. Why is it a two-tailed test? Because our alternative hypothesis was not equal to. So we also have to then look at the left side here and use the p-value on this side, which being symmetric, the p-value is going to be exactly the same thing. Again, this is only, ladies and gentlemen, on a two-tailed test, do you have to account for the p-value on both sides. So basically you need to take 0.2067 plus 0.2067, or ladies and gentlemen, just take it times 2. 2 times 0.2067, and that p-value is 0.4134. Okay, pretty large p-value. Now, how does that compare to alpha? That p-value is greater than alpha, which is 0.05. Now, again, because remember, we divided alpha amongst the two tails. So remember, this p-value was divided also amongst the two tails. So how do we get the entire p-value? The total p-value, we need to make sure that we multiply it by 2. You only do that with two-tailed tests. Okay? So then to finish this up, because we're getting a little long. All right, so let's go ahead and write our final statement here. So since alpha, the p-value is larger than alpha, we're going to go ahead, ladies and gentlemen, and fail to reject the null. Failed to reject h of 0. Now, what this basically says is even though our sample proportion was higher than 16%, it was 19%, it's not strong enough to say that for the entire population, the sample proportion was something other than 16%. So what we're going to say is there is not sufficient sample evidence, and you can just say sufficient evidence if you want to state that the percentage of M&Ms, and why I said percentage, even though it's proportion, our original statement that Mars made was in a percent form. So there is not sufficient sample evidence to state that the percentage of M&Ms, and let's say of green M&Ms, is not 16%. Okay? There just wasn't enough evidence to say that the percentage of green M&Ms is not 16%. It could be. I mean, that could be true, but it's not. And one last thing before we go. Because we're not rejecting the null, we're not saying that the evidence supports that it is 16%. The only way we can do that is to actually take all the population of M&Ms and count the number of, and find the actual true population proportion. We're just saying our sample evidence is not strong enough to say that it's not. It's not saying that it is 16%. It's just saying it's strong enough that it's not, or it wasn't strong enough to say that it wasn't 16%. Okay, next video, let's look at the very last example.